Hi students, welcome back to geology. Today we are talking about glaciers and climate change. First things first, how do glaciers form? So glaciers form from repetitive snowfall accumulating every year. There's little to no melting in between the snowfall, and as more and more material is deposited as snow, it compacts, and that compaction will start to form ice. And that ice eventually accumulates large enough and creates this big mass, which is what we know as a glacier. Right, so in this diagram here, you can see the accumulation zone where snowfall is hitting the slope and then starting to pile up. So the compaction that occurs is similar to the compaction of sediments. And then eventually it turns into this big ice block. And so you can see the snow crystals there on the top right accumulating. And as they are under the weight of the other snow, it starts to compress into ice. So throughout this, we're going to talk about the different types of glaciers. We're going to look at three basic types. There are some combination glaciers that we do see. And in some areas, we have multiple of these types of glaciers. So we might see alpine or valley glaciers, ice sheets, and ice caps. First one here is alpine valley glaciers. So these are going to be located in most mountain ranges. So our really, really high elevation mountain ranges like the Andes, the Rockies, the Alps, the Himalayas. There's a few in the Sierra Nevada that we will talk about in a little bit. But this is where we're going to see these types of glaciers. You can also have them form at lower elevations. So this is going to require a high rate of annual precipitation. We're going to need a lot of snowfall, but it can happen at lower elevations. For example, it does happen in the Olympic Peninsula in Washington. So an example is the Mendenhall Glacier, which is in Alaska. It is 12 miles from downtown Juneau, and this is actually currently retreating, unfortunately. It's about 13.6 miles long, and it, like I said, is currently retreating, as is many of the glaciers on Earth. So as we go through this, you'll start to see that we're going to talk about a lot of the same places because we need high latitudes, we need cold temperatures in order for these glaciers to survive. Moving on to ice sheets or continental glaciers. These are glaciers that take up a very large area. So they can be millions of square kilometers and thousands of meters thick. So a lot of these are going to be found in Greenland and Antarctica. So the Greenland ice sheet is the largest ice mass in the northern hemisphere, and then the Antarctic ice sheet is the largest in the southern hemisphere. The Antarctic is actually separated by two different ice sheets, and we'll talk about what happens if either of those melt a little bit later. So here's the Antarctic ice sheet. So as a whole, it covers about 14 million square kilometers or 5.4 million square miles, and it contains 26.5 million cubic kilometers of material or 6.4 cubic miles of ice. Pretty large, covers basically the entire continent. And you can see on here where there are areas that are losing some of their mass. Some of the ice is being lost and some of the ice is being added to. So the blue is being added and the red is being lost. Here's a look at the Greenland ice sheet, covers most of the continent there as well, 1.7 square kilometers, and this is about 80% of the surface of Greenland. And then you can see Iceland over there, a little tiny guy on the east side of Greenland. A lot of people associate Iceland with having ice, and Greenland does not, but it's quite the opposite. Greenland has most of the ice. There are some glaciers in Iceland, but Iceland is more known for its volcanism because it sits on the mid-Atlantic ridge in the middle of the Atlantic Ocean. All right, then looking at ice caps, these are going to be smaller versions of ice sheets that are going to be found at the tops of mountains oftentimes, which is why they're called caps. So they usually cover less than 50,000 square kilometers. Iceland has several of these, and then the Olympic Peninsula snow dome that I talked about earlier is actually an example of an ice cap as well. In the Sierra Nevada, we have two that are left. We have the Lyell Glacier and the McClure Glacier. The Lyell Glacier was first discovered in 1871 by John Muir. John Muir was a sheep herder that did a lot of exploring in the Sierra Nevada. He helped kind of protect Yosemite and protect the wilderness. And so a lot of the areas up there are known as the John Muir Wilderness, or if you've ever heard of the John Muir Trail, all of those things are named in his namesake. This is the largest glacier that's in Yosemite National Park. It lies on the northern slopes of Mount Lyell, and it's been retreating since the last little ice age, which was around 14,000 years ago. And technically, as of 2013, it's no longer considered a glacier, but in our hearts, we want it to be a glacier because it's near and dear to us because it's so close. So there's a look at it in 1901 versus 2011, and you can see it's lost a lot of its mass. And then the McClure Glacier is also in the Sierra Nevada. It was named after William McClure, which was a Scottish geologist. This glacier is 0.2 miles long, and it covers an area of 0.08 square miles. So it's much smaller than those ice sheets we were looking at. The elevation here is a little bit steeper than the Lyell Glacier, so it's a lot harder to get to. There's not as many photographs of it. And again, it has also been retreating since the Little Ice Age. Right, how do glaciers move? So this is a big part, right? So glaciers aren't just ice and snow. They are moving things that help shape and change the landscape. So understanding how they move is really important so that we know where they're going to be, what they're going to do, and it tells us something about the landforms that we see post-glaciation in an area. So as ice accumulates, it starts to flow downward under its own weight. So with gravity and the added weight of the material, it helps move down. In addition, where there's contact between the ice and the ground, there's generally a little bit of melting that occurs. And where that occurs, it helps glide, the material across the landscape. And so within the thick portion, we're going to see a plastic zone and a brittle zone. The brittle zone is going to be towards the top of the ice. And at that point, that's where everything is pretty cold and it's not under a lot of pressure. So it ends up being very brittle, creates crevasses, a lot of cracks, large cracks along the glacier. And so that is also an issue when we start having water added. It helps get the water down deeper into the glacier, which unfortunately helps break the glacier apart, which we don't want. But then in the center there of the glacier, the thick part, we're going to see a plastic zone where the pressure is pretty intense. And the pressure is helping kind of create this flow zone where material is not breaking. It can actually kind of bend with the movement as the glacier moves down. And so as the glacier moves down, it also starts to pick up sediment and debris and silt and clay and all kinds of other things that then we see deposited later. Each glacier is going to have a budget. So this is just like having a budget for your life, right? I have $5 to spend on lunch today or whatever it is. So with the glacier budget, we are looking at accumulation and ablation. So accumulation is going to be accumulation of snow. So the more snow that turns into ice, we're going to have more glacier. Ablation is driven by temperature, rain, and humidity, which is going to take away from the glacier. And so if you don't have a balance of those, you either have a growing glacier or an unhealthy glacier that is receding. And so if your accumulation, is more, then you're a growing glacier. If your ablation is more, then you are a receding glacier. And so we want to see more accumulation of snow, but as we know or have probably heard, it is not the case with most of our glaciers on Earth. So as these glaciers move across landscapes, they do leave erosional and depositional features. So the first thing we're going to do is we are going to look at some erosional features. Okay, so first we're going to look at rock scratches, U-shaped valleys, and hanging valleys. Okay, so with rock scratches, this occurs when glaciers are moving across a landscape and they have a lot of other fine material, and sometimes they pick up larger rocks and it's grinding against the bedrock. As it grinds against the bedrock, it creates this really fine powder called rock flour. That rock flour then helps polish the rocks that are the existing bedrock, and it leaves behind these grooves that we call glacial striations. And so if you look at that picture in the top kind of middle there of the slide, the rock scratches, those linear lines that you see are the glacial striations. So if you see that in the field when you're hiking, exploring, you would know, hey, there was glaciers here at one point in time that helped create this feature. We also see U-shaped valleys. So U-shaped valleys are created from glaciers eroding previously V-shaped valleys. And V-shaped valleys are created from stream incision. So streams will incise landscapes and create a V, but once a glacier gets plopped in there, it generally starts to carve it into more of a U-shaped valley. And so Yosemite is a U-shaped valley, and so there's a picture of one there for you. And then a hanging valley is a tributary glacier that is feeding the main glacier, and as that glacier retreats and recedes, you start to see a plunging into what used to be the main glacier. And so the example of a hanging valley there is Bridal Veil Falls in Yosemite. There's a few others in Yosemite Valley as well, but Bridal Veil is kind of the most iconic, very obvious hanging valley example there. Then we also see things like horns, arêtes, and cirques. Horns are very steep spires or steep pointed mountains that have been carved by several glaciers around them and kind of left this point in the center. And so the Matterhorn there is an example. There's a photo for you. Arêtes are ridges that are carved between two glacial valleys. So you would have two glaciers on either side, and where they kind of meet, they would create this arête or this ridge of material. And then a cirque is where those glaciers would be. It's the carved bowl-shaped valley that those valley glaciers would have sat in. Moving on to looking at the depositional features. So this is stuff that's left behind by the glacier, not what was carved by the glacier. So in general, the material that is left behind by a glacier we call till. So glacial till is a bunch of different grain sizes ranging from clay to silt to pebbles to boulders that gets left behind in a very poorly sorted fashion by a glacier. These can get lithified and turned into a rock, but oftentimes they kind of stay this kind of mishmash of material, especially if the last glaciation wasn't that long ago, right? Because it takes a long time for rocks to turn, or sediment to turn into rocks. So with glacial till, we can be more specific about its deposition by calling it a moraine. So a moraine is a mound of deposits consisting of this glacial till, and it can form a bunch of different types of moraines. We can see terminal moraines, recessional moraines, lateral moraines, medial moraines, and ground moraines. It really just depends on where and why the moraine was in place. So a terminal moraine is going to be at the end or the terminus of a glacier. A recessional moraine occurs as a glacier is retreating. It doesn't always melt at a super consistent pace. A lot of times there are kind of steps and it stops and then maybe it expands and then recedes again. And so during that, if there is till left behind, we call that a recessional moraine. Lateral moraines occur on the edges of the glacier, so it's the deposits left in kind of the same orientation that the glacier is moving. And then a medial moraine is a lateral moraine that meets another lateral moraine when there's two glaciers kind of side by side. And then a ground moraine is a lot like a blanket of this till material. As material was left behind, it kind of deposited slowly over time and spread out. And so it was kind of this blanket of glacial till. During the melting process, we are also going to see a lot of meltwater create streams in and around the glacier. As this happens, those streams can take excess sediment and pull it down into a lower lying area. When that occurs, we call that an outwash plain. So the outwash plain is going to be a collection of sand, silt, gravel that was all carried down by meltwater streams. Sometimes the glacier will leave behind very random rocks. And so we call these glacial erratics, which are large boulders that are left behind that don't match the local bedrock, and they're oftentimes found perched. And so this example here is at Olmsted Point. That starts with an O, Olmsted. And this is the back side of Half Dome that you can see there, kind of off to the left. This is on Highway 120 as you're going kind of east out of Yosemite National Park. And this is a great example. There's lots of glacial erratics in this area. So there's a bunch of random boulders that are perched here that don't have the same rock type as the rocks that are existing there. And they are found perched kind of funkily, like, why was that rock there, right? So that's more evidence that there were glaciers in this area. Next, we are looking at a special type of lake. This lake is a kettle lake, and it forms as a glacier is retreating. Not all of the ice is melting at the same rate. And so sometimes a big chunk of ice might get left behind in the sediment. If that happens, eventually that block of ice will melt because it's not attached to the main glacier that's helping it stay frozen. And so as this melts, it's creating this depression. So it's already depressed in the sediment, creates this depression, and it creates this kettle lake. And instead of it melting and flowing out like a stream, it creates this lake that's in this little bowl shape from the impression of the ice block. Then we also have eskers, kames, and cairns, and drumlins. So here's kind of a diagram showing you some of these different things. We've already talked about some of them. There's the kettle lakes. There's the outwash plain. We have some terminal moraines on here. The recessional moraine is there. But for an esker, it is a long, sinuous ridge from accumulated stream sediment. So there's stream sediment that has accumulated, and it creates kind of this linear feature that stems from the receding glacier. Kames and cairns are mounds of till in hills. So when there's, a bunch of collection of random deposits of till, those are kames and cairns. And then drumlins are elongated, asymmetrical, teardrop-shaped hills that reflect ice movement. So they kind of show you how the ice was moving throughout the landscape in that teardrop shape. And then a few other glacial lakes we're going to talk about: tarns, pattern Auster lakes, and post-glacial lakes. So tarns are the lakes that fill in a cirque. So remember, the cirque is the valley glacier that's left behind, right? It's right next to the arêtes, which are the ridges in between the cirques. So that's that bowl-shaped feature. And water filling in there from a glacier is known as a tarn. Pattern Auster lakes are a series of lakes between moraines within an alpine glacier basin. These are usually also found in cirques. And then post-glacial lakes are lakes that form next to a glacier because of crestal loading. All right, let's look at glaciation on Earth. So Earth has had 4 major ice ages. It's not to say that there hasn't been glaciation or little ice ages throughout time. These are just the 4 major ice ages. We have 2.5 billion years ago, 700 million years ago, around 300 million years ago, and 2.5 million years ago. So 2.5 million years ago was the last glacial maximum for Earth. And since then, we have been in a warming period. We did have a small glaciation around the Mammoth times. So that would be the Pleistocene. And then it started to recede around 14,000 years ago. So we don't see anything really glaciated in the Sierra Nevada anyway, post 14,000 years ago. So what causes glaciation? So plate tectonics, obviously moving land masses to different parts of the Earth. That's going to create different climates, and climates that are going to be cold enough to support glaciation. And then short term, we're looking at Earth's rotational axis and variations, Earth's orbit around the sun. So As the sun is tilted, the Earth is tilted away from the sun, that's when the northern hemisphere is in winter, and that's when we're going to see accumulation of snowfall and added material to our glaciers. And then as the sun is pointed towards, as the Earth is pointed towards the sun or tilted towards the sun in summer in the northern hemisphere, that's when we start to see more loss of or ablation of our glaciers in the northern hemisphere. All right, so here's a look at the distribution of glaciers 20,000 years ago. So this is as things started to recede. But one of the cool things here is that you can see a lot of exposed continental shelf. So if you look near Florida, near New Orleans and Texas, you can see that like green strip is all material that is currently covered with ocean water. So that is the continental shelf that's exposed when there's a lot more water locked up into glaciers. So the sea level lowers, okay? But when when glaciers are not so vast, sea level rises, right? Here's a closer look at the ice sheets in the United States or in, North America 20,000 years ago before we had warming. It just shows you how far down we saw glaciation, which is pretty extensive. And you can see in our Sierra Nevadas down there, if you look at California, you can see that the Sierra Nevada was glaciated as well. So here's a look at the coastlines 20,000 years ago. You can see that a lot of the coastlines, Florida, East Coast, Europe, Southeast Asia, they had a lot of extra land, right? So this is when a lot of water is locked up into those glaciers, a lot of extra land available. When those start to melt, we lose all of that land. So what would happen if Antarctica's ice sheets melted? So here's a look at the West Antarctic ice sheet and the East Antarctic ice sheet. So sea level change is an obvious effect. So as melting occurs, if we lose a lot of the ice in Antarctica or even in Greenland, we're going to see sea levels rise significantly. If we have refreezing, which would be great, we're going to see sea levels drop. But in general, if we're going to see melting, which is the trajectory we're on, we're going to see sea levels rise. So the next couple of slides, we're going to go through some scenarios about what happens if all of this ice melts. So if the west sheet of Antarctica melted, so this shows you the west sheet, which is significantly smaller than the east sheet, this is what our coastlines would look like. So Florida is losing Miami. Miami's gone. The East Coast is probably losing Philly and a little bit of New York. And then Southeast Asia loses a little bit, and then Europe loses a little bit as well. But it's not too bad, right? There's still a good portion of Florida left. So we still have some livable habitats there, but it's going to displace a lot of people, right? What about the East sheet, which is a larger portion? Well, Florida's gone. A lot of the East Coast cities, they're gone. Southeast Asia loses a significant portion. Bangkok is gone. We're losing a lot in Europe. And this is a problem, right? Because this is the trajectory that we are on. We are going to lose a lot of coastal cities if this continues to happen. And if all of the ice melts, this is what we're looking at. So this shows North America, Asia, and Europe again. Europe and Asia, significant loss. If you look at North America, a lot of our major cities are along these coastlines. We've got Houston, we've got New Orleans, we've got Tampa, Miami, all of Florida's gone. Charleston, New York, Philadelphia, Washington, D.C., Boston, all underwater, right? So it's not just a problem of we're losing all the ice. It's also a problem of it's going to directly impact our coastlines, our cities that are going to be underwater that usually make a lot of money for the United States. That's going to be an issue. You can see San Francisco's basically almost underwater, and then the Central Valley is filling in with water as well. So that excess water, that sea level, is going to rise through the delta and come into the Central Valley, and we will be an inland sea or lake filled if all of the ice melted in Antarctica. So why would it melt? Well, that's from global warming, right? So the Earth is warming, and the Earth is warming because of the CO2 concentration. So CO2 is going to be naturally occurring on Earth, but not at this concentration and not at this rate of parts per million entering the atmosphere. So this is just a trajectory from 1958 to February 2018. And so you can see there's about 100 ppm more just within those few years. So we've seen a significant increase, and we've done a lot to try to mitigate this. But we might be at a tipping point where we've already tipped the scales too far, and all the glaciers they're going to melt when they're going to melt. It's just a matter of trying to buy us time, essentially, at this point. But looking at worldwide carbon emissions from, the early 1900s to today, you can clearly see that there's been a significant spike since the Industrial Revolution. So while carbon dioxide is naturally occurring from volcanoes and other processes on Earth, not at this rate. We've never seen it in the rock evidence, in the glacial evidence, an increase in CO2 concentrations this significant. So it is definitely us, unfortunately. But we can do things to help mitigate it as long as we all participate. So glaciers leave behind evidence carved into the landscape. They leave behind deposits. They leave behind erosional features. So the till is left behind. And a lot of them are actively receding on Earth, unfortunately. And if all the ice melted, many of our coastline cities would be lost. And I do recommend the documentary Chasing Ice. It was last on Disney Plus, from what I remember. So you might be able to see it on there. But if you have some free time, it's an excellent, excellent documentary about a geologist who was taking time-lapse photography of glaciers around the world. And he got some really, really awesome shots. So I highly suggest that if you have time. All right, I will catch you guys later. Bye.